This computer is programmed to sort examination scores into order. It'll allow me to enter a sequence of scores. They're all numbers between 0 and 1,000. So I'll put some in. And I'll do what it says on the screen and put in a negative number to finish the list. Almost immediately, the computer prints out the scores, sorted in a numerical order. So what's been going on? How did the computer sort those scores? And more importantly, how did we program it to do that? Well, to understand what's going on, you first need to look at the way the scores are stored in the computer. And the way we store information inside a computer is to use what we call a data structure. We've chosen to store these exam scores in a data structure called an array. You can picture it like this. There's a collection of places where you can store the scores, and each score is given an index number. The index number just gives the position of the score in the array. So, for example, score 3 is 624, and score 7 is 489. Size is an integer variable containing the number of scores currently in our array. So that's how the computer stores the information. To sort it, the computer must execute a program. So how do we go about designing such a program? We use top-down design. Now this is where we start. It's called the top level of the design, and it's the very broad strategic plan of how we're going to proceed. 1, read in the scores. 2, sort the scores. And 3, write them out again. In fact, you might think that this top-level design was so general that it didn't tell you anything at all. But in fact, it tells you quite a lot. You read in all the scores before you sort them, and then you sort them all before you write them out. You don't mix these activities up. So that's the top level of the design. In the top-down design procedure, we take each of these 3 steps and refine them in stages. The refinements lead to what we call a design of the solution to our problem. That design must then be translated into our programming language, Pascal. In this program, we're only going to refine the middle section of the design, and we'll take this part of the design all the way to the Pascal statements. This one middle step is expanded into 6 steps. And to indicate that it's a refinement, we've numbered the steps using this dot notation. So the single step 2 is turned into these 6 steps numbered 2.1 to 2.6. And you keep on expanding until the steps are sufficiently detailed that you can express each step as a single Pascal statement. Here, for example, steps 2.3 and 2.4 aren't sufficiently detailed. So we expand each of them again. The single step, 2.3, becomes these 7 steps. And the single step, 2.4, becomes 3 steps. Now, in some cases, you might need to continue this process even further, with yet more levels of refinement. But in this case, we'll find that we don't need to do that. Our design is now sufficiently close in its level of detail to the programming language Pascal. So that's the process we use. Start with a short top-level design and refine the steps again and again until they're detailed enough that you can write the program directly. And what we're going to do is go through all this in detail so that you can see just how we arrived at this final program. So to start with, we'll go back to the very first stage that we want to refine. Sort the scores.
These are the scores we're dealing with, stored as an array in the computer. How are we going to sort them into order? All we need is a systematic method. Well, suppose we start like this. First, we look down the array for the smallest score. It's the one in position 6. So we'll use this value as the first element of a new array, which will contain the sorted scores. Then we look down the array for the next smallest score, ignoring the one in position 6. The smallest one now is in position 4, so that becomes the second element in the sorted array. Then look for the next smallest score, and so on, until there are no more scores left to sort. The new array will then contain all the scores in order, which is what we wanted. So that's one way of sorting the scores into order, and it's a systematic way, so it's suitable for use by a computer. But it's wasteful of space inside the computer's memory, because ultimately every score will have been stored twice, once in the original array and again in the sorted array. And in fact, that's not really necessary. There is a way of using this process that only requires a single array. For that, the scores have to be arranged in a rather clever way. This is the sorting process halfway through. Although you can see two arrays, we could squeeze the scores into a single array. That's because on the right, we're just using the upper part of the array containing the sorted scores, and on the left, we're only interested in the unsorted scores. Those unsorted scores could fit below the sorted scores, and then they'd all fit into a single array. To use this idea, we have to devise a technique which splits the array into two parts, an upper sorted part and a lower unsorted part. And to do it, we'll use a marker to indicate the first unsorted element in the array. We start with our array containing the original data, and we look for the smallest score. As before, it's in position 6, but this time we don't use it to start a new array. Instead, we put it in the first position of the existing array. Of course, that leaves us with a problem. Where do we put the original first score? It needs to go back into the unsorted part of the array. Anywhere will do, and we've just created a convenient space for it, the place where the smallest score used to be, and that's where we put it. So what we've done is to exchange the smallest score with the score in the first position in the array. The first score has now been sorted, so marker must move on to position 2. Now we can repeat the process. Find the position of the next smallest score, and of course we only have to search through the lower part of the array from marker down. Then exchange the smallest score with the score at the top of the unsorted list, the score indicated by marker. And then update the marker to point to the next position. And keep repeating this until all the scores have been sorted. So, rather than using two separate arrays, we can just use a single array. And now that we've decided how we're going to sort the scores, we can apply top-down design to turn the idea into a program.
Here's our top-level design. What we want to do is refine the middle step, sort the scores. Our sorting technique is repetitive. We do the same sequence of operations time after time, once for each score. So the essential feature of this technique is that it contains a loop. And that's what we specified in the refinement. These two steps, 2.2 and 2.6, mean that all the steps between them are repeated several times. Well, how many times? Well, if you look at step 2.2, you'll see that we're told to repeat the operations within the loop while the scores aren't completely sorted. You keep on performing the actions while the job you're doing isn't completed. But we also need to specify what those activities are. Those are the steps within the loop. And we can remind ourselves what they are by going back to the process. First, find the smallest unsorted score. That's the smallest score in the unsorted part of the array. Then exchange that with the score indicated by the marker. That's at the top of the unsorted part of the array. Of course, that's not quite all. The new score is now sorted. So the part of the array containing unsorted scores is now smaller, and we must update the marker to show the new position where the unsorted scores start. And that'll just be at the next position down. So those are the steps within the loop. Find smallest unsorted score, exchange smallest with score at marker, and move marker to next position. What we haven't done is performed any initialization. And this is something you must always do for variables which are updated within a loop. You must give them some sort of starting value. So what needs to be initialized? Well, let's look systematically at the steps inside the loop. First step, 2.3. Find smallest unsorted score. This is a process dealing only with the scores. And since the scores have already been read in at step 1, no further initialization is needed. What about step 2.4? The smallest score has just been found in the previous step, and it has to be exchanged with the score at the marker. But which is that? Somewhere, marker has to be set to refer to the score at the top of the unsorted list. And if we move on to step 2.5, you can see that marker has to be updated. So marker must be initialized prior to executing the loop, and that's step 2.1. And since, to start with, the whole original list is unsorted, we start the marker at the position of the first score. And now we've refined our original step 2 into 6 steps, 2.1 to 2.6. This is the next level of the top-down design. Now, of course, we'll have to refine it still further, but before we do that, let's remember that there's another aspect to designing a program. We also have to build up a data table.
During the design, we'll be building up this data table. It lists all the items we'll need, and for each item, it gives its identifier, its type, and its description. Now, the way to construct a data table is to build it up as you expand the stages of your design. We haven't finished our refinement process yet, so we wouldn't really have completed the data table. But let's look at the entries we would have included so far. This second entry is the array we use to hold the scores. So we've called it score. To define its length, we've used this first item, limit, which is the number of elements in the array. Now, limit isn't a variable, it's an integer constant, and it stays the same throughout the process. It has a value, say 100, given to it at the beginning of the program, and that value can't be changed without amending the program. So the value of limit is the maximum number of scores that the program can deal with. Of course, we might want the program to sort fewer scores than the maximum number. In that case, although the array might have 100 elements, we'll only be using some of them. In the example at the beginning of the program, we only used the first 8 elements, so we'll need another variable, size, to tell us the actual number of scores that we're using. It's an integer variable, and it's a variable rather than a constant, because we don't know its value until the scores are read into the array. We've used one more variable in our design so far, that's marker. That's the index to the first unsorted score. And that's the data table so far. Let's continue with the refinement process.
Here's the design we have so far. Let's see how we refine it. 2.1, set marker to position of first score. The first score is in position 1 of our array. So in our refinement, we set the marker to 1. Next, loop while scores not completely sorted. We've got a variable called marker to tell us when we get to the end of the scores, so we'll loop while marker is less than size. Now, it turns out that steps 2.3 and 2.4 need much more refinement. and we'll come back to that in a moment. But step 2.5 means we must update the marker, and we do that by adding 1 to it. We increment it. So there are 2 steps we need to refine, 2.3 and 2.4. We'll start with step 2.3, find smallest unsorted score. Well, let's remember what happened when we saw this take place. We looked through all the unsorted scores and remembered the position of the smallest so far. At the end, we finished up with the position of the smallest value in the unsorted part of the array. So, to find the smallest unsorted score, what we have to do is search through the unsorted part of the array. And that means checking each element of the unsorted array in turn. That's a repetitive process, a loop. Well, here's the loop that we're going to use. But what do we do each time round the loop? We check each unsorted element. If it's smaller than the smallest one we've found so far, then we have a new smallest one so far. And when we've checked all the unsorted elements, the smallest one so far will actually be the smallest. So what does that look like written down? If the current score is less than the smallest score so far, then obviously we have a new smallest score so far. And that means we must change the index of where the smallest score is. We must set the index of the smallest so far to be the index of the current score in our loop. Well, this presupposes that we've already got a smallest score so far. Well, how do we get that? Now, when we start this process, when we go through the unsorted list, the first score that we meet must start off as the smallest score so far. So let's initialize this loop by setting the index of the smallest one so far to be the first element in the loop. And that's pointed to by marker. Now, if the first unsorted score is the smallest one so far, then we have to compare it with all the other unsorted scores. We know exactly where they are, so we can use a for loop. We loop for the current position from one below the marker all the way down to the end of the list. So, at last, we've refined step 2.3 into these 7 steps. But we haven't finished yet. Let's look back at the earlier stage of the design. As well as step 2.3, we also need to refine step 2.4. And here what we want to do is exchange 2 values, the smallest unsorted score and the score indicated by the marker. Now, in Pascal, we can't do that all in one go. We have to use a new variable, a temporary variable, and perform the exchange in stages. So that gives us 3 steps as a refinement of our single step 2.4 using our temporary variable. And this is the stage our design has reached. Now we're ready to turn it into Pascal.
Here's the Pascal program corresponding to our design. Let's see how we've arrived at it. There's a program heading which gives the program a name. We've called it sort. Below the heading is the declarations part. Then, between this begin and the final end, there are the actions corresponding to our design. Let's look at the declarations part first. It corresponds to the data table that we've been building up. These are the data items we're using, one constant and several variables. If we just leave out the description of each item, what we get is almost exactly the declaration part of the Pascal program. So here are the declarations. First, there's a constant, limit, with its value written in here, once and for all. Whenever limit appears in the program, it will always be equal to 100. Then come the variables, the keyword var, and then the identifier of each variable, followed by its type. And that's the declarations part of the program. Now let's look at the actions part. There will be some more to go in here, but as we haven't done the design for that yet, let's move on to the piece of design we have completed, sorting the scores. This is the Pascal version of our design. And because we went through the top-down design procedure, the structure of the Pascal is the same as the structure of our final refinement. There's an outer while loop, which extends from this begin to this end. And here's the inner loop, a for loop, which controls just a single if-then statement. So when we reach the final stage of refinement, we already had the structure of the Pascal program. We just had to translate line by line into the special words used by Pascal. For example, set marker to 1, that becomes marker takes the value 1. Loop while marker less than size, that becomes while marker less than size do. And the translation into Pascal matches the design practically line by line all the way down. Set temporary variable to score at marker, that becomes temp takes the value, score at marker, and so on. And that's that, our Pascal program. There are still the read and write pieces of program to be designed and translated, but let's assume that's been done and that the program's complete. All that remains is to test it.
The program's in the computer. Let's see what happens when we try it out. I'll run the program and enter some numbers. It seems to work. The numbers come out in order. But will it always work? Well, we could try entering more sets of numbers, and eventually we might become confident that it did work. Well, that's one way to test computer programs, but experience shows that it's not a good way at all. The reason is that it's not systematic. When you provide test data for a program, you shouldn't just generate it at random. You should deliberately select it to test all parts of the program, especially the boundaries of the program. I'll show you what I mean. Here, the main structure of the design is a loop which puts the first number in the correct place. And the way it does this is by performing comparisons. So the test data we provide should check these features. For example, what happens when we enter lots of numbers, the maximum the program will accept? Or just a few numbers, or say 2 numbers, or 1 number, or no numbers at all? That will test out the loop. And what happens if some of the numbers are equal? Or if they're all equal? Or if they're all in order to start with? That will test out the comparisons. Well, I'll just check what happens when we enter very few numbers. Let's try 2 numbers. So I'll execute the program. Put 2 numbers in. And they come out in order. In fact, it always works. So what have we done? We had a problem of sorting a set of exam scores by computer. We tackled the solution to the problem by top-down design. And the design we came up with started with a brief top-level design, which we successively refined. First, we decided that our design would be a repetitive set of actions. So we introduced a loop. We put some flesh on the actions inside the loop and initialized the loop. We then refined each of the steps in turn, and finally turned that design into a Pascal program.